Yeah, so yeah, we finished talking about the lists. We built an array list that was, we built the ordered list, unordered list, and indexed list. And we then briefly, very briefly talked about the idea like, well, we could implement this with a link structure too, because why not? And for those of you that were in lab yesterday, well, that's what you did. And for those of you in lab today, well, that's what you're gonna do. But at the end of the lab, or pardon me, at the end of the lecture, I was trying to figure out why the hell my thing wasn't working with when I was like overriding those operators, right? So I discovered what it was, and it was a very easy solution. So wait, where do we go? Array list? No, array indexed list? Yes, so plus. What I had to end up doing was define the function as constant. So if we go up here, basically all I had to do was say, wait. No, but then that was constant. Did I not fix it? Yeah, pardon me, make sure I didn't hit some undos. I'm building it just to see if it works. Okay, cool. So you might remember when I called this function down here, when I used the operator plus, like it was getting mad because it was saying something about get. Constant versus reference t, blah, 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 blah. Long story short, the problem was when we do something with the operator, we basically want to be like, we want to make sure like the fact that the other one that we're getting, const, means like we shouldn't be altering the other one. Like we're getting a, right? Which is a reference to another array index list. But because I put it as const, it basically is enforcing that like, and we're leaving it alone. We're making sure it's safe. But then in here, when I called get, I didn't set get as constant. So up here, I said, no, don't worry. I put this little constant keyword after get. And if I jump down to get, you'll see it's there as well. That basically says, don't worry. We're not going to, this function is not going to change anything. So just make sure that everything's left alone. So now if I go back here and then I tested it. So I made my list. I made my list 2, which was a copy of my list. And then I did the, I added them together. Like I did plus with array index lists. Oh, I already built it. I'm gonna hit run. And we'll see 5, 30, 66, 3, 5, 30, 66, 3. Why? Well, because my list is 5, 30, 66, 3. I made a copy of it, and then I added them together, and well, now my list 3 is that. So it works. Isn't that neat? We now define what plus means for array index list. And one other thing that's pretty cool is, and this actually was brought up at yesterday's lab by Johannes about like, well, hold on. If we have an array ordered list, like for example, let's go back at array, whatever, I'll just explain it. You might remember in the array ordered list, well, whenever you added something, we needed to guarantee that it would be added in the right spot. So if we go to array ordered list, oh, that's the wrong one, array ordered list. When we did add, we basically did this, right? Where we're checking, well, is this thing at list index less than element, right? And what's the type of element? Well, it's T. It's generic. It can be anything. And Johannes brought up a really good point of, well, what if the thing of type T doesn't have like less than defined for it, right? Like how can you guarantee that less than works? Like sure, clearly it worked when I did it with integers, but integers have an ordering, right? Less than is an operator that works with integers. But what if I put in student objects here? And if I'm asking the question, well, what if this student object, like is this student object less than this student object? What does that mean? C++ isn't going to know, like, well, what does less than mean in this context? So what we can end up doing, just like we did here as a way to solve that problem, but again, other languages have a way to deal with this better. What we can end up doing, array index list, is just like down here where I define the operator plus, I can define the operator less than for the objects of that type. So it would know, assuming I implemented it correctly and effectively, it would know what less than means in the context of those types. Anyways, we won't need to get into that too much right now. But yeah, we can define less than equals to, greater than equals, and not, whatever. We can define a lot of things. Anyways, let's talk a little bit about computational complexity. So here's my array list, right? What's the computational complexity of remove first? Right? What is this? Someone put it in the chat or yell out, whatever. Let's see if you can think about it. Think of like big O. Come on, someone's got to know. N, yes. Why? Well, because if we look at the code, we take this out, great, that's an order 1 operation, it's constant time. But then you remember we have to do that like shift down. So we got to move everyone down. And how many things do we have to move down? Well, however many things are in there, and let's say there's n things in there. Yeah, we need to shift everything, order n. What about remove last? What's the computational complexity of that? Come on, wake up. 1, yes, correct. Why? Well, we remove the one thing and then, well, all we have to do is decrease the count. Easy peasy. What about remove an arbitrary one? So I don't really know where the thing of type T is. What's the computational complexity of this? N. Well, what do you mean depends, actually? This is interesting. What do you mean depends? Well, yeah. But why does it depend? You're saying it depends, but why? So, yes, we need to do a search. But here's the funny thing, right? Depends on where we remove from. I'm not sure it does. Let's have a talk about this. Because let's say I've got a bunch of things. 0, 1, to n minus 1 because we started counting at 0. These are indices. If I find it, let's say I find the thing at location t, at some arbitrary index k. Okay, I found it at index k. I had to do a linear search. And how many things did I look at? Well, I had to go from 0 to k, right? So if I go 0 to k, I mean, I looked at k things, right? But then now I'm going to have this gap at location k. So what do I have to do? Well, I have to shift down. How many things am I going to have to shift down? Well, what do we see? Some fraction of n minus k. Well, it would actually be n minus 1 minus k because we started at 0. But yes, we would have to shift from location k to n minus 1. And how many is that? Well, it's n minus 1 minus k. So in total, same thing. Yeah. Well, you know, when we're talking about computational complexity and big O notation, you're actually right. So here's the thing. If we had to do a linear search from 0 to k and then shift everything from k to n, how many things did we move? Like, what was the total amount of crap we had to do? N. We still had to do n. Sure, we might end up removing something that's in the last position, but remembering that's the worst case scenario, and we also have to search to it. First, what's the computational complexity of grabbing the first thing? Which should be easy. It's order 1. Last, order 1 as well. Why? Well, we know first is always at index 0. We know last is always at rear minus 1. So it's just a quick look up. Whoop. How about contains? What's this one? What's the computational of this? What's big O of this? N. Absolutely. Why? Well, we're going to have to search through a linear search. And the only way we can guarantee we found it is if we look at all the things. And hell, the thing might not even be there. We will only know it's not there if we looked at all n things. Now you might say, well, sometimes you might get lucky and it might be the first thing. Well, you figure maybe for every time you get lucky here, you also get very unlucky. And maybe every time you get lucky here, you get very unlucky here. So basically, on average, how many times are you going to have to look at things for the search? Well, it's going to be like on average, n over 2, right? Because half the time it'll be before and half the time it'll be after, right? But here's the thing. 1/2 times n, what is this? Well, this is a coefficient. And what do we say to coefficients? We say, get lost. I don't know. There. So really at the end of the day, find calls, which is linear search, yeah. Ordered lists add. Ooh, what's the computational complexity of adding something to an ordered list? And yeah, why? Well, because we got to do the linear search for where it belongs. And then we're going to have to shift everything up too. So it's order n. Linear search and shift n. Unordered lists add to front. What's that one? One. I'm not so sure you're right. Because n. It's going to be n. Yeah. Oh, wait, because we got to shift everything. See, you said, oh, wait, I'll give you that one. We're going to have to shift everything order n. Unordered list, add to rear. Cool. You give me this one. Hey, there you go. Add after. Well, that's going to be a linear search and a shift, so order n. Index list, add at a given index. Ooh. So we don't have to do a linear search anymore. So what's the computational complexity of add at a specific index? What do we think? N. Why? Well, because if we want to add here, well, we're going to have to shift everyone down 1. And the shifts are, I mean, on average, we'll have to shift like n over 2 things because, you know, who knows where it'll end up. But at the end of the day, we don't care about the half. It's order n. Wait, why doesn't linear search plus shift n squared? Because it's not n times n, it's just n plus n. I mean, effectively, you're right, Cole, is they're not looped. So the linear search plus shift is, well, if we did one linear search, how much work is that? Order n. And then if we did a shift, how much work is that? Order n. So at the end of the day, it's just n plus n, which is equal to 2n, not n squared, right? And again, we don't care about that. And really, as we know, if we want to get super fancy and talk about like T of n, which is a little more precise than the big O, we do know that it's going to be 0 through k, and then k to n for the search and then the shift, which in total is going to be n stuff anyways. The only way, it's like n squared pops up when it's like for each thing, we have to do n new things. And how many things are there? Well, there's n. Where in this case, it's only like for each thing we have to look at it once and do something. And once we start looking at more algorithms that have something that's like an n squared complexity, it'll become a lot more obvious. Things will fall into place. And that'll happen once we get to like searching and sorting. Whoop. Index after T. Yeah, index list, add T element. Well, that just adds it to the end. Index list, set an element, add an index to something. Well, that's order 1 because this overrides something or overwrites something. Index lists, get something at a given index. Well, that's just order 1. Index lists, index of an element. Well, that's a linear search, order n. Index lists, remove at a given index. Well, that's going to be order n because we're going to have to shift stuff down after. Index lists, this fancy thing, well, that's the same thing as like get, which is just order 1. Now, you might say, wait, we implemented that interesting circular array thing, right? Where with the queue, that eliminated us from having to like shift all the time. So wouldn't that be better? And well, the answer is maybe that's a great idea. And we could totally implement it that way. There is nothing, nothing stopping us from doing that. But I suppose it's a bit of a question of like, how much will this matter? Is this actually an important idea? Little thought question for you. And of course, we made an array list. Can we do a linked list? Of course we can. Absolutely. We're not going to look at it here, but you could do it on your own. And in fact, you'll do it in lab today if you didn't do it yesterday. Things we need to remember. The following slides are, oh yeah, whatever. I'm just gonna skip over this because we did it before. This is just inserting before, after, add, whatever. Blah, 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 blah. Deleting, yeah. We already saw all this stuff. Yeah, think about the computation. So we talked about computational complexity for the array implementation. I'm curious what the computational complexity for all those operators are for the linked implementation. Anyways. Yeah, so there we go. That's it for lists. And now I believe we are moving on to a topic where I'm just going to start and end and we're going to be happy. Yes, perfect. I'm going to blitz through this one because it's not going to be like, I'm going to show you something neat you can do in C++, but I'm not going to worry too much about this in the course. So the point of this lecture is see what structures are, see what enumerators are. So a structure is just a really simple, easy way to just kind of like collect and hold some data together. It's kind of like making an object that just has some fancy attributes with it without having to make a full object. We can make a structure. And you can do this in C as well. Yeah, it's like a watered down version of a class. So here's the format. If I want to make a structure, this is what I would do. The keyword struct, then the name of it, open squigglies, and I've got my close squigglies with the semicolon. And then I would just name all the types of the things and the variables of the information I want to hold on to. So here's an example. I might have a person structure that has a string first name, string last name, integer age. There. Then, if I make one, I could do it like this. I could say person A equals, and then the order is important, right? This is going to be the first thing listed, the second thing listed, the third thing listed from this, right? 1, 2, 3. 1, 2, 3. 1, 2, 3. And then if we wanted to get the attributes out of this, it's just like this. It's just like this. Kind of like we would deal with an object if we had a public attribute. Just, okay, what's the first name? What's the last name? There. Great. Cool. So you can see it's a really simple, easy, simple way to just have like an object with a couple of attributes that are, it would be like they're declared publicly, but it's, look how much easier it is to define. And here's another way you can make it is, well, you can just do it like this. Create a person B and then say, okay, BF name is this, B's last name is this. So just kind of like an object, right? Except this is you're calling the specific attribute. This is the name of the structure or the instance of the structure. And then a third way of doing it is, well, let's say you want to use pointers because we all know that I love pointers. Create a new person and then just do it the same way, but use the little arrow thing because it's pointer and that's how we deal with pointers. So by the way, this type of syntax is the same as it would be with an object if the object's attributes were made public. And let me show you what I mean. So if I go down to a student object, I guess I need to go to the student header. See how I set these as private. If I decided, you know what, I don't want them to be private, I'm going to make them public, right? If I were to go back to here, and I guess I'll include student. Okay. If I were to go back here and say, okay, student, I like pointers. Student. So obviously we know we call the functions by saying, okay, name of the object, the instance of the object. If it's a pointer, we use a little arrow, and then we call the function, and then of course we need our open bracket, close bracket. Well, it's the same thing with attributes, but attributes are variables, they're not functions. So you don't use the parentheses there. You would do something like email equals, and this would work just fine. So it's the same syntax as if it was an object with the structure. But of course you remember that, well, you know, in practice, for cleanness of code, we don't like to make our attributes public if we don't have to. We like them to be private, and then we use the getters and setters to make sure we're interacting with the attributes the way they're supposed to. Anyways, just an FYI. So the syntax is like the same as objects. And you can have structures in structures. Like I made an address structure that also has within the structure, one of the things is a pointer to a person called the addressee. And then, I'm doing it. Yeah, whatever. Structures as parameters. You can make structures a parameter, just like objects and whatnot. Here I'm making it a reference, I guess. But you can do that. And again, if it feels like I'm going fast, I know, I'm kind of doing that intentionally. I'm just showing you like, hey, this is a thing. And if you ever want to do it, you're aware of it and you can go figure it out because it's actually really similar to what we've been doing already. Yeah, blah, blah, blah. Now, enumerators are also kind of cool. It's a way to make like a new type for integer constants, but in a neat way. So it's probably best to explain this with this example though, because otherwise it's going to sound like, wait, what? So let's say, for example, I want to make an enumerated thing called a day. And the values I want to have associated with it are Monday, Tuesday, Wednesday, Thursday, Friday. But you'll notice that these aren't in quotes, right? These aren't strings. These are effectively like variable names. So really what it's doing is, okay, so we have a day and Monday is actually, Monday is a variable that means 0. Tuesday is 1, Wednesday's 2, Thursday's 3, Friday's 4. So what's the point? Well, let's say I made something like this. Day, someday equals Tuesday. I can, I can say for int day equals Monday, day is less than or equal to Friday, do something, print out the day. That might seem silly, but then again, look how readable this code is. Like I look at this and go, oh, well, clearly they're just enumerating over the days of the week. So this code has something to do with the days of the week. Another example of where this might be really handy is if you think to the assignments 2 and assignment 3, where I'm doing like the get neighbor, right? Well, I could have done this in like an enumerated way where I was like, well, 0 is actually like up. 1 is to the right, 2 is down, and 3 is left. So I could say like check up, check down, instead of saying check 0, check 1 or something. I heard a boop. Does it start at index 0 or 1? I believe 0, but we can test that pretty easily. I'm pretty sure it's 0. So what's the point? Well, let's say I had something like daily sales. Well, here, yeah. Same idea as the previous slide. I've got an array of daily sales, 1, 2, 3, 4, 5. Maybe my loop is designed in such a way, well, print out the daily sales. And if the day happens to be Tuesday, well, put this extra thing of like, well, maybe I expect high sales because on Tuesdays I just have high sales. And then otherwise just keep printing out the other stuff. So again, a contrived example, but here's an example of where it works. And really it's about like code readability in this case, because look, like again, I look at this. Oh, if day equals Tuesday, oh, perfect. Imagine I said if day equals 1. Like sure, there, 1. If I said day equals 1, sure, we could know what that means. We're the programmer. But now I look at this and there's no thinking involved. Oh, it's Tuesday. Yeah, if day's Tuesday. Oh, perfect. Yeah, okay, days of the week. So the code becomes very readable at this point. And that's it. And for those of you that had experience with C before, I wouldn't be surprised if you have experience with this already. All right, now we're moving on to some of my favorite stuff to teach. Raise your hand if you have ever, I'll just do this. Raise your hand if you have heard about recursion before. And leave it up. Now, raise your hand if you have been told that recursion is scary and mean and hard. Two people. You have been misinformed. I think that the biggest issue people have when learning recursion is they come in with the expectation that it's difficult. It's not. If anything, it's almost more like a more natural way of looping stuff. Teachers never tell us that. That's just... A lot of people will say, oh, recursion is so scary. Especially other students will say that. It's bullshit. It's not that bad at all. There's no tricks when it comes to recursion. It might feel like there is, but there are no tricks. The only rule is, like everything else in this class, the silver bullet is, what does the code say? Follow the code. And even better, grab a sheet of paper and a pencil and follow the code. Because there's no tricks. That's it. People will come, I'm stuck. Okay, show me how you drew it out. Well, I didn't do that yet. Well, go do it, because then you'll solve your problems. Anyways. Recursion. I love recursion. So the call stack. This is an important feature to talk about before we get into recursion. And when I say the call stack, when I say stack, I mean stack. But unlike a stack that we implemented in the code, like an array stack or something, this is a stack, but it's not implemented. It's the system stack. And I'll show you what I mean. So what is the call stack? What's a call frame? Whatever. If you've ever done some debugging, you may have seen something like this before. Let's say you put a breakpoint and you ever call the debugger in Visual Studio, you might see something like this. And this is your call stack. And basically what it says is, oh, okay, so in the main function on line 14, we called the function, level order. And on line 243, I called the function level order again at some other line of code. And then I called the function in queue on another line of code. I don't know where it is. And then on line 122, I called the isEmpty function and whatnot. What we're seeing here is functions that were called inside of functions, inside of functions, inside of functions. Eventually, isEmpty is going to return. And then when it gets returned, well, it gets popped off the stack. So every time we call a function, it gets pushed onto the stack. Every time we finish a function, it gets popped off the stack. So it's a stack, but it's used to store information needed for the methods and functions when the program is running. And it's going to hold on to information like, okay, the local variables, the formal parameters, the return values, the memory address on where to return to, and all these extra fancy things. Actually, that's basically it. So the top of the stack is the current method function currently being run by the computer. So if we go back here, it's isEmpty. That's what's currently being run. When a method or function is called, a new call frame is activated and it's pushed onto the stack. So the stack is full of call frames or activation records. And it's going to hold on to the return value, although that's not going to be known when it gets called, the local variables that exist in that function, the formal parameters, which is just basically the function parameters, and then the return address. Some function called me, which exists somewhere in code or in memory. So when I'm done, I need to know who to give my return value back to and where to find them in RAM. So a call frame contains the information the current method needs in order to do its thing. The local variables are created and stored in memory, allocated by the call frame, and it will deallocate it for us, right? Unless it's a pointer, the pointer will be deallocated, but the thing that the pointer points to might not be deallocated, so we have to be careful about that. Remember, dynamic static memory. The parameters, again, the return value, and the memory address for it to return to. What I mean by this is, if I called a function, let me just go over here. If I go look at a function, okay, here I'm calling expand capacity, right? And in expand capacity, no, oh, I guess it's in the base class. So array list. When I call the expand capacity function, the expand capacity function, where the heck is it? Okay, it has no parameters, so it doesn't need to store that. It has no return value, right? But what it's going to need to do is, okay, look, I need to make a new local variable that is a pointer to something of type T, new list, great. So it's gonna create this for me. And that's the only local variable it creates. Actually, no, I guess it creates a local int I for the loop's purposes. But it creates this local variable. This is an attribute for the class, so it didn't create that. So the only thing that this call frame that's activated for the expand capacity function is going to actually really need to keep track of is like, well, there's no formal parameters, there's no return value. We have two local variables we're going to have to make sure we deallocate, which it will do. And it needs to know where to return from. Basically, who is the calling function and how do I get back there? So the previous thing on the stack. In this case, it actually is a pointer. So the new list variable will get deallocated and the I will get deallocated automatically. But if this thing being pointed to was a pointer to an object that we just didn't need after the end of this function, we would delete it. Now, in this particular case, it's kind of funny because we don't delete the thing that new list points to. We delete the thing that list originally pointed to. But long story short, the pointer variable gets deallocated easily. The thing that it points to does not. So we have to be careful about that. And this little local variable here, the integer I, will get deallocated for us. But the same rules that we have always been following about pointers and things in dynamic memory still apply here. Okay, call frame contains the information, blah, 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 blah. Okay, so here's an example, a really simple little example of what's happening. So let's say I call function 1, and here's my stack, and here's my bottom of the stack. Currently, there's nothing on the stack. All right, I call function 1. Oh, I guess I have my main function too, where I call function 1. So what I'm going to do, I hit run on my program, immediately the main function gets pushed onto the stack. And then I go in, and now I'm here. Great, I call function 1, push that onto the stack. Okay, so now I'm here. Okay, I print out stuff, I print stuff out, I call function 2. I jump down to function 2, create a call frame, perfect. Run this line of code, run this line of code. Oh, now I call function 4. Push it onto the stack. Okay, here. I print out stuff, I print stuff out. Oh, I'm done. And I'm not returning anything, so what am I gonna do? Well, I'm gonna pop from the stack and return to the calling function, which was right here. So I'll carry on, I'll print something out, perfect. Oh, I'm done. So function 2 is now done. What do? Well, pop it off the stack. So then function 2 is done, I go back here, okay, perfect. So, because remember, that call frame, function 2's call frame, knew where the calling function was, which was right here. So it carries on, prints something out, calls function 3. All right, jump down to function 3 and push it onto the stack. Print something out, I'm done, return to the calling function, which is right here. Print something out, I'm done function 1, go to the calling function over here, which was main. So now I'm here, oh, now I'm done, pop, main, program's done. That's how it's gonna work. I did that quickly, but we've got a couple more examples, but it's not too crazy, right? So does recursion just make a large stack one by one and then pop it all one by one at the end of the condition is met? I'm 99% sure you're correct, but just to be safe, let's not talk about recursion right now, but we will talk about the recursion in the context of the call frame in the next set of slides. But yes, it's not even like, oh, it creates a large stack. It's the same one system stack. And when a function calls itself, it just keeps pushing those things onto the stack. So yeah, that's what that is. Now, when C++ pops things off the stack, it knows how to get rid of those things. It knows how to deallocate things in memory, like the local variables, the integers, the characters, the floats, the pointers. But it does not know how to deallocate the things that the pointers point to. Because if the thing that the pointer points to was something that you allocated in dynamic memory, we got to be careful. We got to make sure that that's safe. Now in our expand capacity, we did it safely because, I mean, we created a new object in dynamic memory, but we wanted that to be the thing that the attribute pointed to, but we needed to delete the old thing still. So if you're looking for a rule of thumb, the rule of thumb is follow the same rules we've always been following. It's just, I'm putting the warning here about like, just remember, when we delete pointers, we're deleting the variable that holds on to the memory address, but not the thing that the pointer points to. Nope, wrong button. Okay, yeah, pointer variable storing the address, yeah. So, oh, actually this goes to your question. Here's a function. Look at this function for a second. What happens if I call this function? Well, what do you think will happen if I ever call this function? Well, I call my main and pretend, okay, I've got my main here. There, and I push this onto the stack. So here we are. What's gonna happen here? In fact, Johannes, what do you think's going to happen here? The only reason I singled you out is because it seems, yeah, and we're actually going to see a lot of we's. So let's think about this. Again, there's no magic here. Nothing weird is happening. It might seem like something's weird happening. It's not. You're thinking too hard. What does this say? Okay, call the function uh-oh. Okay, perfect. We're here. What do I do? Print out we. Okay, great. And then what do I do? Oh, call the function uh-oh. So create a new call frame. Oops, actually, I forgot. I needed to do that one first. So now create a new call frame for uh-oh and go to the function uh-oh. Okay, perfect. What do I do? Print out we. And then call uh-oh. Okay, great. Create a call frame, push it on the stack. Okay, go inside that function. All right, print out we, now call uh-oh. All right, perfect. Create a thing on the stack, and so on, 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 and so on. Do we see a problem with what I have done? What's the problem? What have I effectively done here? Order infinity. Yeah, basically, yes. Oh, and Felix, yes, you see a problem. Too many E's and we. Well, what's the max stack size on your computers? That's a very good question. In fact, let's have a little bit of fun. Let's see what'll happen if... So, the stack size can be gigantic, but when you hit run on a program, your program's going to look to set aside a chunk of RAM, and every programming language is going to be a little bit different. So like if you're in Python, Python will only give you so much RAM to work in. So you'll run out of memory a lot quicker than you would in other languages, but other languages will still have limits. And has anyone here ever heard of the thing called Stack Overflow exception? Raise your hand if you've ever heard the phrase Stack Overflow before. Of course you have. This right here is an example of a Stack Overflow. Basically, your computer's going, uh-oh. Clearly, we've got an issue where we're just pushing things onto the stack, and the stack's growing and growing and growing. We have a Stack Overflow exception. Something bad happened. So, I'm going to go to my hello world. I'm going to delete everything here. In fact, let's just make uh-oh. Oh, I closed it already. Well, whatever. I'll do it again. Void uh-oh. And then we'll call uh-oh. Perfect. And then in here, I'm just going to call uh-oh. And I'm going to hit run, Control-Shift-B. So, actually, no. You know what I'm going to do? I'm going to have it print out. Okay, I'm going to write this slightly differently. So here's what I'm going to do. I'm going to make uh-oh take an integer, n. I'm going to print out n. But then here I'm going to give it 0. And then the next time I call it, I'm going to give it n plus 1. Actually, I'll start it with 1. So basically what this is going to do, let's think about it. The first time it goes, it's going to call this function. It's going to print out 1. Then it's going to call uh-oh and pass the value 2. So now n is 2. Print out 2. Then give it the value 2 plus 1, which is 3. So now n is 3. Print out 3, 4, 5, 6, 7. Basically, we've created a loop that counts. So let's see. I wonder when it'll quit. So the problem here, I'm going to stop this. The problem here is printing out is actually remarkably slow. So maybe what I'll do is I'll say if n mod, where's the, there, mod 1000. Basically, if it's a multiple of 1000, then I'll print it out. Let's try this one. Uh-oh. It looks like it's hanging because it's angry about something. So I'm going to run the same thing in debug mode, and we'll see what happens. Come on, what's going on here? Loading up the debugger thing. Takes for, okay. Look, we're hanging. Why? Unhandled exception, stack overflow. Well, why? Well, first of all, we'll stop this. Clearly, it ran more than 4,000 times. So it looks like we were able to push somewhere between 4,000 and 5,000 things onto the stack. But look, here's my call stack. If I go all the way down to the bottom, we call main. Then on line 26, right here, we call the function uh-oh. So there, we go in there. And then on line 20, we call uh-oh, and then uh-oh, and then uh-oh, and then uh-oh. And then look, it's probably hard to see, but look how look, I'm hitting up. You can't tell, I'm scrolling up currently. And look how slow. Can I copy this? Copy, can I copy everything? I'm gonna copy, then let's see. If I just open a new file here. Sure, text file. Look at that. It looks like it had 4,793. There. That's how many things we pushed onto the stack until it said, I'm gonna stop now. Anyways, hopefully that was fun for you. And because I love recursion. Recursion is amazing. So recursion, we're gonna take advantage of the call stack like Johannes brought up. I mean, you're absolutely right. It's basically, you keep pushing things onto the stack, but if you never stop, you're just gonna run out, you're just keep pushing things on the stack, and then your computer will finally say, we got a problem. Anyways, we'll wrap up here. If you don't have lab today, have a good weekend. Otherwise, I'll see you in lab.